Thank you for introduction. Let's start it with other introduction to maybe set up what you can ask what makes sense task. So I'm doing state set machine learning. Before I did a bit of work in machine learning in the industry for surrogate modeling. So now, in the past year and a half, I'm more focused on things related to approximate tensor network contraction, right? And a bit of my way from to this problem was decoding toric codes. So there is a work done, and there are a bit of small subfield of people doing machine learning for this. So today we'll try to go through it, right? And it's mostly talk about machine learning part, right? And if be more precise, it would be a bunch of neural network designs for decoding concretely toric code, right? I could always say what is extendable to other type of codes, and pretty everything is extendable to topological codes, or maybe more broadly for stabilizer codes. But I will just want to, because it's Kusov's seminar, you all guys work on very complicating things, but this is just a bit of bunch of machine learning, UvA. Right, so plan is following. So I will give you a bit of background to set up what people already do, and did pretty well job, of course, without machine learning for decoding toric codes. And this all we could see as we take some existing approach and try to see what we can learn inside this algorithm, and then try to see if it's something learnable or not. Okay. So let's also, of course, I'm sure you're all experts, but just for convenience of pipeline of talk, I will briefly set up what is our goal, what is decoding, what is code, and everything like this. So we have some logical state, right? And similarly as in classical, almost before I define things formally, everything in classical error correction code. We have a state, we would like to protect it and from the noise of the environment. And so for this, we need to some redundancy. Redundancy introduces several physical qubits. Then something happens, noise acts, and we say, okay, now we need to make some readout of information that we can, and using this information to decode and see if it was correct or not. And of course, we have here a bit of a quantum world, and we have some special organization of what we can read out with measurement circuit, right? But it's at this point to say just some bunch of classical information which we could extract, and then we could pass it to decoder, right? So it's possible that our measurements are noisy, so we do several rounds of measurements, and then we take this all, or take just one and put decoder. And what else we could put? So these measurements we will call syndrome, and we of course could put also the decoder, the probability model of error channel. So basically what noise act on each qubit, and then maybe probability model of how error spreads when we're starting to measure things, and the structure of connectivity between our, basically the graph of parity checks. This all we could take and put to the decoder. Okay, so through the talk and most basic model of noise channel is depolarizing model. Basically, we're saying, okay, we have a bunch of physical qubits in some graph, and per qubit we're saying either identity applied or sum of the probability is equal probabilities. Also, almost all machine learning work, we assume perfect measurements, so I will assume here also. Right, so now, okay, we need to define basically what code we will use, and we will focus on the toric code. So what we do, we take a square lattice. On each edge, we put a qubit, right? Then we put square lattice with periodic boundaries. on each qubit, then each vertex and each face we could associate with a small contractible loop plaquette, just blue and red squares. Then of course, because we on a torus, there are two more loops on each primal and dual lattice, which we will associate with logical operators. And basically this is our code. Right, so then errors which happen, we could think about. I like to think about them. They just put color on the either edges or dual edges. Then we have strings, right? And these strings we could catch on the endpoints. So this example, on the left some error string, which is like both in primal and dual, and on the right just everything right, but I kept the syndrome, which is equal to endpoints of the strings. Okay, so now let's go to like what non-trainable approaches exist to decode. So I like roughly could split them in two big parts. One big part is okay. We somehow need to match because we are okay. So we on that. If we on our code is on the planar graph, right? Everything could be boiled down to matching endpoints, right? Because if we somehow made a perfect matching between each endpoint, we have some valid representative with valid syndrome. So we could say, okay, this is our correct. Right? Then always boil down how we matching. So there are like groups of approaches based on either union find or minimum weight perfect matching algorithms, which I briefly mentioned next. And of course, if you have like, because we have primal and dual lattice, usually people split the solution between like first they solve on primals and solve on dual. There are a lot of algorithms which is somehow make iterations from this, right? Because one solution is influenced on another and so on. Right, other possible branch of the solution is saying, okay, hey, what we want to do, we want to just estimate some, find most likelihood correction to given syndrome, right? And of course, because we see only endpoints, right, we could deform it with any loop. So we need sum up over the loop, over the whole loops, and this could be like some represented in either tensor network or just like make kind of renormalization style flow of coarse lattices. Then you just exactly like approximately try to sum up big exacts.
Just to clarify, can you go back to the previous slide? It's finding hard to see the colors. Like, is it so basically for there is like a sequence of edges, and then the syndrome is at the endpoints of the edges. So like if you have like a pink edge, then the blue things are what you read out, and vice versa. If you have like a blue edge, then it has the pink edge.
Okay. So let's focus on this too. So on each edge is qubit, and yeah, we could say that okay, if X power is in blue, if Z power is in pink, or vice versa, doesn't matter. Right. So let's say blue is primal lattice, so some error act right here and there, and we could because we design checks, right? So these small plaquettes on the dual lattice. Dual is green. So usually you can think about them as star operator, like it's easier to see the case. This is this small square around here. It can catch this end.
And so, like, if I have these four pink ones, these pink circles, then is it fine? Like, it could be caused also by vertical edges instead of horizontal. Does that matter?
So you observe.
Yeah, this is the only thing you
observe, right? So because you only observe endpoints, and then kind of decoding game is saying, okay, you can have variety of compatible with syndrome strings, right? Because if you add any loop, the endpoints doesn't change. And so
you want to just pair up these pink dots and the blue dots, basically.
You want to pair up, and then maybe then it was a bit briefly. Let me just, I'm talking very fast, I guess, so we find to repeat more details. Sorry. So okay, we have lattice, right? On each lattice or lattice on each edge we put qubit. On each qubit acts depolarizing channel. So we randomly put x, z, y or identity power unit. Right, so we can think about this process as it's drawing some string. Right, so then what information we can preserve with this lattice? We can say, okay, let's our logic state will be the presence of some non-contractible loop. So then, if some chain cross it, right, it's could trigger it. Say, okay, here is it. Right. Also, what we can do with chains, we could catch endpoints. Right, because we need like our parity checks to commute with logical operators, so they both need to be loops. So this is a bunch of loops, and these loops can act on chain with endpoints. Right. So then, because you are like after measurements observed on the endpoints, you say, okay, I'm fine with any string which match endpoints. Right. We could like, if exponentially many on the lattice size draw them. But then they differ by the either they're crossing even an odd number of times some non-contractible loop, which you preselect or not. So this is task for decoding. Right, and then some bunch of approaches is saying, okay, let's do the following, let's find the chain which is the least weight. Right, because it's in a way most probable. Right, and then we find it, and then we could say, okay, look, which non-contractible loops it's crossing, and extract logical information back. Or we can go reverse, or say, okay, we really want probability of each cassette. Right, so we would like to sum up all possible strings, which these endpoints over all loops, but with fixed logical part in it, with fixed presence of non-contractible loop. So here it will be 16 variants. Sum up, maybe we sum up approximately, and we get as result not error correction string, but just logical outcome. We could compose this. We have logical part. We could say, okay, we just let's take as correction anything with without logical, just any matching, then put it back. Okay. Does it clarify this? Cool.
Is the minimum weight perfect matching, is it also the maximum likelihood decoder, or is there something?
It's a bit confusing, at least for me, but I think usually people in literature call maximum likelihood decoder the exact summation. So
it's not, it's more like the maximal free energy when I
Yeah.
think about it that way. But they're more or less related in this particular setup.
Yeah, if in this term, so this is minimum weight is like free energy, maximum free energy, and then maximum likelihood decoder is partition function of this free energy. Yeah, and then of course one to others like is related. If you make temperature very high, you want to get to other. Okay, so then also what we can do is we could range a bit these decoders, right? In what terms? So of course, when we're decoding, we need to decoding fast enough that new errors doesn't occur, because if they occur, like our work become much harder. Like instead of two-dimensional problem, you're now three-dimensional. Like it is not good to do. So we need to be fast, and so we have a trade-off between fast and slow. Right, and this also a bit restrict algorithms of like, either if you want to be fast, you need to do something very locally, and if you would like to be like more accurate, you necessarily need to allow yourself more global computations, so you will be a bit slower. Right, so this is our guys. Right, so the fastest one is union find, which is I will show a picture in a sec, but roughly, you can imagine like as you said, like you just need to match them. So you can stand on each syndrome circle, start to grow. As soon as something match each other, okay, is your solution. It is very greedy, but it is very fast. Right, a bit more complicated is, but also could be viewed as growing. That if you start to grow clusters, then see how they merge in which order, and it's a bit of this like all filtration of information you provide a solution. Right, then we're moving further, saying okay, we could in this spectrum we could use like any of these two guys and try to iterate them or to try to provide additional information. And for example, belief matching decoder is firstly make just some passes to update prior of errors, right? Because easy to see if you have some particular syndrome here, it's very likely that some like a probability of edges that some Pauli put here is not like not the same as was before. And then finally we have tensor networks things. So basically, because again we planar, we can start some. We can relate syndrome decoding syndrome to just some partition function. Then we run planar graph. We run some boundary MPS, right, with fixed bond dimension psi, and say okay, we are done. Right, a bit maybe a caveat here that of course if you start to make bigger lattices, and you want because you got a lot of bigger distance, so probably you also need to increase the bond dimension, right? So because this, I guess, it is slow, right? So then other possible, right? As I said, type of like divisional type of decoding, either it account for correlation between X and Z errors or not, or say X solve separately. There's any of them. Not accounting, you can make accounting. Okay, so let's start with a bit simpler problem, right? To get to, because like both union find and WPM would be seen as just grown from the peeling decoder. So what is simpler problem? Let's imagine that now we know the exact places where error occur, but we just don't know what completely occur, like which Pauli. It could be an identity. So we're given some local area, but not given what happened. Right, but then decoding is very simple because if everything is uniform, you're happy with any solution. So you just take this like supporting of error H, make here the spanning tree, forest if they're disconnected. Time, and you say, okay, now just recursively from the like, dangling edges, you're going forward, we're flipping the syndrome, right? So you look on the dangling edge, or you say, okay, so this is, was it here syndrome 0, 1? If 0, just remove it. If 1, okay, next vertex flipped, so become 1. If it was 0, 0 was 1, and recursively you can go until you have empty set, and it will be because it's a tree. Right, and then like MWPN and union find can be viewed as using this routine. And so I will not like describe the how exactly algorithm like works in most efficient way, because like this also just motivates the neural decoder. But just to like as a spirit, you can think about both of them like this, that both have a start from syndrome as a cluster separate, the like single syndrome in each cluster, so it's odd. We need to connect it with something. So we start to grow. On each iteration, we increase by half edges. And the special event when two clusters submit. Right? They a bit differently than decide what to grow and what to not. For example, union find, like as soon as some cluster is become even, it stops to growing, and only odd clusters grow. And MWPM like all the way, but then when it goes solved and finding a solution, they say, okay, on each subcluster we could run in this sequence subcluster on this peeling decoder, because you're a bit more certain about locations now, and aggregate it to get solution. Right, maybe important outcome is all of this things is saying, okay, so the problem of decoding for toric or specifically, and like for any planar decoding graph is planar, could be think is something as matching, and matching you could do like very locally, right? So okay, this is that, and this motivate like this, I guess. I very like this work because it's very simple, but it gives a very nice result. So it's work by high maintenance of like scalable neural decoder. So what we have, we again have same lattice of checks and qubits, right? And some qubits, he's saying, okay, some qubits are special, right? Because if you have very big lattice and your noise regime is far from threshold, you will have a lot of very local excitations, which actually you don't need to solve the whole global matching problem, just solve very locally, right? And then maybe do some, because it will specify a graph for matching a lot, right? So just imagine that if you have a check node and like just two, for example, syndrome alarmed, right? And they're in the distant one edge. Of course, there is no need to run any like the rest graph you don't know, but to correct all this, you can immediately say, okay, just draw this one edge will be not very bad solution. Right, so what he do? He's saying, okay, you have big lattice of all checks, and if you see on this syndrome, and like around each syndrome, there are nearby qubits, right? So around each check, there are like 4 of them. So let's just predict the Pauli error concretely for this qubits around each of the check. Right, because it will probably specify the problem for next decoder like union find on WDPM, and it will be faster, and it also will try to a bit correlate X and Z errors. So what he do, like from like he do very simple thing. He say, okay, let's, because we're solving locally, let's take just patch, just like cut the small thing, like array of syndrome. Put it inside neural network and output like 4 numbers for each type of Pauli. Right? We do this. If it's we take most likelihood prediction, we say, okay, this qubit is now with this error, and we modify the syndrome accordingly, right? With spinning decoder, because if we know what is happen, you just can propagate syndrome. And then the rest of syndrome you put either on like on any other decoder, but because here is aim for speed, right? And we a bit spend time on preprocessing with this machine learning. We want to put it in union find. Right? And from machine learning perspective, he used like super simple thing, right? Just take fully connected layer, like not a lot of them, like 5, take this big matrix, map it with some nonlinearities, stack of layers with to single number, and like optimize. Right. So a bunch of things, I guess, could be made more efficient in some way, because like if you do it for each qubit, it's a bit easy to each qubit, I mean around check, right? So it's a bit easy to reorganize that you like just make convolutions, and you basically output not one number but like same grid for qubits, right? I guess it would be just a bit faster, but it works nicely, and like you could see that union find like threshold was like this, and it's shifted like efficiently, right? And for reference, so it's on toric code and depolarizing noise, and the WPN threshold is like this, like 0.15, and the network is around 0.18 and something, and like theoretical possible, like the best is a bit lower than 0.19. So it is kind of very good solution, right? Because in a very small cost of time, and I would say like in very small cost of training, like from hardness of like designing the algorithm in a way, right? simple solution, you get very nice results. Okay. Is there any questions?
Can you go back one slide? So like the input of the neural network is this 5x5 patch, and the output is, because like it predicts, is this like the error for one specific qubit?
Yeah.
So do you need to run it for like
Yes.
every edge in the?
So as I said, like as he described it, he takes this neural network, make it like I don't know, 3 or 5 fully connected layers. And so just matrices, put a simple matrix, multiply by matrix, like nonlinearity and so on, and then roll it across each qubit. Right, but same thing, a bit reformulated is to say that you have convolutional neural network, and you output like says like same size with, I mean, like qubits, right, on the square lattice horizontal vertical for each vertex, so you output same grid with 2 channels. Predictions. Yeah. Maybe like one thing here is that the way how he designed it like this is that because maybe you don't want to apply for every patch, but yeah, in paper there is nothing about it. Okay, so other type work is saying okay. There is like kind of renormalization group approach for this type of problems, right? Because we on the big lattice, we have prior probability of noise on edges, and we have syndrome. Based on syndrome, we could like join lattice on pairs with bigger unit cell and redefine somehow the probability per edge, and then do it until we get the like small lattice size which we could sum, say exactly. And then this is kind of easy do in this problem. So we have just the lattice, we define unit cell be 2 by 2. So syndrome inside we just course by summing up modulus 2. And then we say, okay, edge we will join, but we will find the probability of it. Find it probability versus edge, we need to sum up everything out with capable with syndrome. Like, okay, this is a big task, but we could pretend that we did it already for all the rest. A part of lattice, right? Put it around this some selected cell. Then for the other parts, okay, obvious. What is answer, right? You just sum up like those things around red and output, and you do it iteratively for each cell, and in this, if it's converged, you get your new abilities per edge. Right, so it's a known around with here, but so don't say, okay, we could actually try to learn it. So it's I would say nice approach, not very nice results, but also one of the point of attack, right, which is nice to do is he said, okay, I could do this, and I could train like some neural networks to predict the outcome of this renormalization procedure. Right? So to predict like this PP getting probabilities per edge. So he trained neural network on these results, and then he like combines saying, okay, you give me lattice with this neural network trained on BP results, cars lattice, and then put some dense layer and make output. Okay, so far we saw some like algorithms, like trainable, non-trainable, and all neural networks. Ideas would say, okay, let's take some existing algorithm and try to beat like zero bias it or use it structure to like, make something learnable. So in case of like Decoder, you learn how to course the edge probabilities. In case of union find, you make a pre-processing of syndrome before it, right? And it somehow works. So, right, and it's good because it's very local, it's fast, and like for both of them, you use something already known, which is good decoders. right? But a bit of problem, which I think is this that right, what you can approximate at most, right? So you cannot hope to be sufficiently maybe better than like MWPM or elevated MWPM because you just do essentially mostly same thing, right? But also, right, in terms of speed, it's a very questionable like result, right? Is it what will be faster? I would bet that like okay, there are a bunch of folks which design special hardware for this type of neural networks, which is say okay, it's very fast, but you can do this also with this non-trainable algorithms, and you can design to be them very fast. Right, so then we try to say, okay, let's learn a neural network from scratch, and let's try to approximate it maximum likelihood decoder, right? So the exact thing. So some like papers which I mentioned above suggest that it's quite not possible, right? Because if you just take a syndrome and you would like to output not like error probabilities, but logical cassette, like it will not scale like about any reasonable place, like 5, 7. So I also tried it, didn't work, and it's easy to see why, right? Because if you, it's very like, first of all, like it's like very complicated problem itself, right? You need to sum up exponential on the larger size number of loops to output cassette probabilities. But also the learning itself could be quite hard because if you start to learn around threshold of your possible decoder, which you don't know yet because you didn't know it will be very hard to learn. But if you push like error noise level big, like very small values, you will have very sparse signal, right? You will have almost no very sparse signal of number and balanced number of logical errors, so 0 of them. So it's require a bit of small work here to say, okay, but like because we on very large lattice, we could design a bunch of symmetries which we take in account, and usually it simplifies the learnability of problem for neural networks. So let's try to do this. Right. So for this we need to a bit recall and formally define what will be symmetry here. Right. So again, recall we are looking on the toric code. Right. We have LBA lattice on each H qubit. Right, and we are given, let's say, as matrices like parity checks and logicals. Like parity checks small loops and logicals non-contractible loops. Okay, so then we could a bit formalize this, just looks like writing, right? So each error string which I told it's a Pauli operator. It we could say to make from it binary string, right? We just say okay. This is A for X, B string for Z, B, we write like this, right? Then we say, okay, if we have 2 error strings, we're just interested if they commute or not, right? Because to catch endpoints, it's actually, it should cross the small loop odd number of times, which is same statement as saying that these 2 strings anti-commute. So we could just write it and see, okay, so this is our symplectic form, let's take it. Right, and all like addition here is modulus 2. Right, and then if we do it, I could formally like say, okay, now I'm just working on the space of B strings, which is 2 times big number of qubits because primal into lattice. Okay, and instead of omega, I will just use brackets because no other product used. So just like use brackets. Okay, so what does it mean we are given a code? It means that we given the stabilizer subspace, logical subspace, which is iterators, right? And we given some commutation relationship, right? We all stabilizers are commute, so their product is 0. All stabilizers with logical commute also 0, and only like non-trivial outcome is just like logical crossing other logical, but so what we need to do, because like not commute only X and Z, we need to primal cross the dual, and geometrically it's also easy to see that okay, crossing it's mean like horizontal, primal horizontal crossing to vertical or vice versa. And so it's everything in pairs here. Okay. So then, because of this, we could say, okay, because it's a symplectic form, right? So we have the whole space of 2n. We have logicals with like orthogonal friends, and then we have same orthogonal friends for each stabilizer. So basically, it's just error string which ends on each specific stabilizers, and all of them start from one specific selected point, at which we will anti-commute from it. And we can call this pure errors. So they commute with everything, but selected stabilizers. So to do this, it's very simple. You just solve a linear system. That's it. Okay. So why this basis is useful for us? Because it's like very useful, easy to see what is our outcome of commutation, right? If I give you an error string with coefficients in this basis, it's immediately to extract. Right, but also it's like nothing more than saying that it just some loops and we can detect crossings. Parity of crossings of everything like even or odd. Right? So then if I have error string, I would say, okay, so I have a bunch of coefficients across each generator of vectors space, right? And there are some examples. So if I would like to extract syndrome, I will just like where error string with one of stabilizer. If I would like to extract logical information, I need to pair it with some logical, but a bit reverse. So if I like to know presence of vertical primal, I need to pair with horizontal dual. Right, but and here is a bit of maybe interesting starts. That okay, if now I know this, and deform logical with loop. All right. So still I could infer what's the result. Right? It will, because it's linear, so it will be the same logical part plus the value of syndrome on the plaquette in which we deform. Right? In this fashion, we could right, by adding a bunch of plaquettes, we could shift the logical and then saying, okay, we can answer given like one logical information about one non-contractible loop. We could say syndrome say about crossing each non-contractible loop. Right, and this gives us kind of like rule of horizontal vertical translation and rotation. Right, you say, okay, if you want to something like select other logical, it's old logical plus the column of the whole stabilizers, and then you still know how to make a result. Right, you just add the sum and goes to. Right, so and then we could use to find the symmetry of exact decoder. Let's go line by line. So gamma sigma was noted before, it's like coefficients of like logical part and syndrome part. So what we want to evaluate, we say, okay, let's sum up over all strings of what? Of probability of particular string. Check if it's have correct syndrome, and check if it have logical coefficients that we probability seeking of. That's quite clear. So then we could say, okay, if we have some action on this error, right? For example, shifting or rotation, and let's denote it like representation of J-acting, right? And try to put it everywhere. So in the first term, it's easy to put because of we just assume by assuming diplomatic noise that the error probabilities are uniform on the lattice. So if I have some particular error string and then I shift it, nothing changed, rotate also nothing changed. So okay, this is fine. So then we could note it here under pairing, it's also invariant under like actually any same permutations, right? Because like easily geometrically, you see if you shift one string and shift other string, you would like to count the crossing, nothing change, and same rotation. So if you do the same, nothing change. So we put everything here. Then we say, okay, right, we could just redenote summation because it's summation across every strings, and we just left here with these guys. Right, but then this we know, right? Because okay, how like will change if I translate a plaquette. It's the same as I say like adding the plaquette. So okay, just change peak value, reverse value. If I translate to right, pick the value is left of syndrome or rotate. So you just act on the matrix of syndrome values. Right, and this logical operators a bit more tricky, right? Because but the geometrically it's again very easy. So the most maybe complicated parts if shifting, but this we already discussed, right? Shifting to be realized is just adding the bunch of plaquettes, and this by linearity you know how it depends from syndrome. And then also like rotation, just swap horizontal and vertical, and yeah, you can also do duality transformation, like exchange primal and dual lattice. Right, and all this just give us a law that if you want to approximate exact decoder, you need to approximate, not need, but it would be good to have like of your approximation property that approximates, follows the simple symmetries. Right, so if you somehow modify syndrome, there is an action of how you remove the logical output to keep result constant. Okay, so then how to implement it? We just need to extend usual things. So let's do this quickly. So what we have, we again have syndrome on the lattice, and we would like to do convolution, right? But now let's also do convolution with filter, which is also stated to small patch of lattice. So now like just not just like matrix and matrix, but lattice and lattice, right? And this just arrange a bit like syndromes on primal and dual. Right, so of course this input syndrome is 0, 1, and our convolution filter on lattice is real values. Right, we can draw like here, but we could also store as two channels. Okay, and then convolution we all know what, so we just put around each, just translate the filter, put it across each parity check node, like here. Here is maybe a bit interesting that like primal and dual will interact directly because they will be in the same patch time to time. Right, so then we need to do this not only translation equivariant, but on the group of permutation of lattice, so P4M. Right, how to do this? We do just in 2 steps. So we firstly uplift from the just lattice coordinates to the group coordinates, and then okay, we have both on the group. We just convolve. So it's like usual convolution, but the first time, right, to estimate value not only like on the syndrome point, like lattice point AJ, but also like acted by say rotation, like rotated, not rotated, like 90, so and so on. For layers, you just say okay, filter is also act for rotation, right? So yeah, discrete lattice it's very easy to rotate. Right. Also, like final operation to conclude this is to say, okay, we need somehow get 16 numbers of which what we do. Right? If we just follow usual recipe and just sum up everything, like across, let's say, special dimension, let's focus for translation here. On special dimensions, then it will be invariant. Right? So, but we know we need something not invariant, but depends on the sum of the parity of syndrome. Right? Because again, it's the same. This example is logical. Right? If you translate logical, so you need to sum up the whole column of the syndrome and see if it's 0 and 1, and this will the logical information here because they are just equal to sum. Right, but it's okay to do because you just say, okay, while I would sum, I would also just flip back what I'm doing. So for each possible, let's say, translation, we calculate either we need to flip like it or no. Right, and then when averaging the results of neural network, we do this. Yeah, that's it. And because, right, if we now apply one more time, flipping, it will go same tricks, like go through the sum as circular and keep invariant. So finally, bit of results, right? So it's so for on the y-axis, y-axis is logical accuracy. On the x-axis is a noise level, a bunch of lines. On the up, it's a curves and decoder. So it's a very fine grid, just to show that I'm very finely run, right? So it's because for neural networks, it's always like question, what if we behave crazy in between? So it's not. It's very much better than MWPM. I would say like better than any other neural decoder, right? And also as a caveat that usually people with neural decoders, they do train per each lattice and per each noise level separately, and they output this as threshold. But I would just like train once and then apply a bit higher, a bit lower in lattice sizes because it's convolutional. It's possible for all range of noises, so it's perform very smoothly.
Right, is there a pseudo threshold somewhere there? I can't really spot it. The minimum weight perfect matching has this little crossover thing around the M. Do you have a similar thing somewhere, maybe a little bit lower? Or?
So, like, if we just visually, I don't know. So what I call threshold here is just a procedure to define pseudo threshold which you run and you like regress or some polynomial with respect to like noise level minus threshold, and you get results like this.
Oh, so the green line is.
So green line is this fitted medium quadratic polynomial over the p minus threshold.
Oh, okay. But what threshold? That's an unknown that you then solve.
Yeah, you feed them.
Okay. Oh, okay. Yeah.
So pretty fine. So right, and then green lines, it's actual lines. Oh, sorry, not green is fitted, and like all blue and purple.
Oh, okay. Okay.
Is actual just evaluation, right? So maybe just like this would be easier. Yeah, so like on the top. Oh, it's all bunch of different.
Only sanity, capital L was the number of physical qubits, right? Or the side length.
Side length. So
Side length. Okay.
number of physical qubits is squared.
Okay.
And yeah. So here we train on lattice size 17. So this is just some degree of parameters number, right? And this results for this level of noise because it's just selected because it's threshold. The threshold on WPM, it's like tensor network threshold. It's a threshold of, I guess it's Merz work union find plus machine learning, and this is I forgot if was this threshold terms. Right, and then you like train on 17 and apply for 17. Let's say same for 1921, and get same information as in plot, but in.
Okay. Yeah. Fair enough.
Okay. Yeah. Like that's it. So maybe as a wrap up of like all. Right. If someone need to do this, it's still a bit unclear for me because so as a good result, I would say okay, if you put like just put symmetries correctly, define problem correctly, put a bit of training in it, you can get really good decoder. Right, but then of course the whole counterpoint is that good in what terms, right? In terms of threshold, maybe it's not very interesting because maybe people don't want like higher thresholds that where like they would like good results, like in not so high noise regime, good and very fast, right? So in this, you're saying, okay, I would better like make system more robust and apply it very fast union find and correct there. Also, like from practical point of view, maybe right, it's not very interesting results because okay, was so some things that are easy to adapt, for example, like leakage during the measurement, right? It just correlated noise model. You could put it here just as additional input on width. You put number of your noise model, and then still all equivariance is the same, because you shift also like noise model, right? But for example, if you would like to do several rounds of measurements, it's already not so easy to design fast machine learning decoder, right? Because you now have problem in like 3 dimensions. It's yeah, and then maybe it's okay for me. It's still like a bit of open problem if anybody needs this, or everybody just like like you can just use MWPM, for example, if you need like more accuracy, and then WPM very like would apply it to the several rounds, or like there is online versions of it, right? When you have like, it's usually what you have stream of new syndromes, and you just add magic not like stably. Yeah. So maybe one shift on which like machine learning could be useful for like, decoding codes is more complicated codes where there is no simple correspondent with matching problems, like color codes or like even a 3D toric code. So we did a bit of preliminary work on 3D toric code. It's much harder. It somehow works, yeah, but it's much harder indeed. For color codes, it seems more interesting direction a bit, because it's a bit more easy. You can still be 2D, and you can like design similar things as I told here for the Equivariant decoder. I didn't try. Yeah, also it's fine know that to see, okay, it was toric code, but for any planar and any like not qubits. So I tried also for qubits for 3-5 levels. It also works. So the outcomes that okay, it works, it could be done, but to be like interestingly applicable, you need to somebody to tell you maybe interesting code setup, not for which not regular decoders are so good, maybe so fast. Okay, thank you for attention.